Recording. Okay, so if you don't have any questions, then I'll just start. Okay, so I think, as I promised, let's prove this spectral decomposition theorem today. So that's spectral decomposition theorem. So it just says this, let E M be a Hermitian bundle. So we just fix one smooth Hermitian vector bundle over M. So this M is closed oriented Riemannian manifold. And so we assume there exists a P E. So B a kind of, okay, elliptic. Pseudo order D positive. Then we can decompose in the following way. Then there exists an orthonormal basis Yn from 1 to infinity, Yn belonging to C infinity of E, P of Yn equal to lambda n Yn of L2 of E. So as it's indicated, this orthonormal basis consists of eigenfunctions of this operator P. Right? So that's the first part. So these are the eigenvalues, these are eigenfunctions, they are smooth, and this is an orthonormal basis for this L2 of E. This Hilbert space is a Hilbert basis for this. That's the first part we want to prove. And the second part, okay, so and also lambda n. And because I'm not saying this is positive or negative, right? This could be first order, for example. In that case, it would have positive and negative eigenvalues, both. But the absolute value of lambda n goes to infinity as n goes to infinity, right? First thing, but in part B, which is, I mean, contains this already, we say something much more about this growth of these lambda n's, right? So I want to say that order lambda n's, like by, you know, absolute value of lambda 1 less than equal to absolute value of lambda 2 less than equal to absolute value of lambda 3, so on. Then there exists a constant C and a delta positive such that absolute value of lambda n is bigger than or equal to C n to the power delta. So not only these guys go to infinity, in fact, they go to infinity at least of some polynomial growth. I'm not saying delta is an integer, but at least of some polynomial growth. So this is a very, very important estimate for, I mean, initial estimate for us. Of course, later on we will give a much more precise estimate than that, but for now, this is the estimate that we need in order to proceed. Okay, so this is the orthogonal decomposition that we discussed, and we want to prove it, right? I mean, spectral decomposition. Okay, so proof, let me start here. So we can consider P as a bounded operator from some subgroup space to another subgroup space, right? P from H, B of E to H0 of E. This is L2 of E, by the way, right? This is L2. So if you consider your pseudo-differential operator from this subgroup space to that subgroup space, then it's bounded and Fredholm by ellipticity, as we proved. Okay, so then it is bounded and Fredholm by what we did as a result of ellipticity. I said elliptic, right? Somewhere. Yeah, elliptic. Right. Okay, so then it means that it has finite dimensional kernel and finite dimensional co-kernel, right? So kernel of P, so dimension of kernel of P is less than infinity, and the dimension of co-kernel of P is also less than infinity. So, so it follows that P, if you restrict it to this part of the silver space, which is the orthogonal complement of the kernel, then it's injected there. Right? So let's take orthogonal complement of the kernel of P. And then it goes to image of P here, which we know is closed in L2 of E because it's a Fredholm operator. So it's a closed subspace of L2 of E. So this, so let me just see, this is in L2 of E. So this operator is invertible by definition. This P is invertible. Okay, so let's call the inverse of this to be S. Let S from image of P to kernel of P orthogonal be an inverse, or the inverse So this S, we can extend it by defining it to be 0 on the orthogonal complement of image of P. Just defining on L2 of E, and then 0 on the orthogonal complement. And it's still is going to be a bounded operator. So this S, by the way, is called a green operator. S is a green operator for P. It doesn't matter right now, so extend it. To a bounded operator S from L2 of E to this space, which is here in E of E, right? As I said, by defining it to be 0 on the orthogonal complement of kernel orthogonal complement of the image of P, right? So which is here. Okay, so this is a bounded operator. It goes there, and then I compose this operator with the embedding of HT into L2, there's this embedding, right? To take this embedding, go into L2 of E. Now, by relic, we know that this guy is a compact operator because we are over a compact manifold and everything. So this is a compact operator by relic lemma, right? Okay, so it follows that this composition is a compact operator because multiplication of a compact and any other bounded operator is again compact. It's a two-sided idea. So that's a compact operator. So now if I consider this S as going from here to there, it's compact. And it's also self-adjoint because it's essentially an inverse to P, which was self-adjoint. I picked it to be self-adjoint. So I've got a compact self-adjoint operator from L2 to L2 now, right? So that's what we have. So this is compact. So S is compact self-adjoint. So I can use a spectral theorem to give a spectral decomposition for L2 of E, because that's what we proved, right? I mean, second lecture, I guess, we proved the spectral theorem. So, spectral theorem for compact self-adjoint operators implies that there exists these functions, I mean elements, yn belonging to, I mean, to E, such that, okay, so first of all, these are eigenfunctions of this operator S of phi n is equal to mu n, right? Is equal to mu n phi n, right? And L2 of E is, and they form an orthonormal basis, in other words, for L2 of E, these guys. And L2 of E, you can just say is direct sum C phi n over n, and then so orthonormal basis. Because I said orthonormal basis, even to say this is redundant. I already said orthonormal basis for. So I don't even need to say this. Okay, to use. Okay, so we have got an orthonormal basis consisting of eigenfunctions for S with these eigenvalues. And of course, because it's a compact thing, so mu n, of course, you see this goes to 0, right? That's what we know. Because it's a compact operator, so its spectrum has to converge to 0. Now, of course, these mu n's are inverses to lambda n's, because this is the, this, if you take this equation, this implies that, P of phi n is equal to mu n inverse phi n if mu n is different from 0. So the places where S is equal to 0, which would be this finite dimensional subspace kernel, image of P orthogonal complement, that we don't care. They correspond to eigenvalue zeros, and but in the rest you have non-zero eigenvalues, and these are exactly lambda n's. Okay, so I get these lambda n's. And since mu n absolute value goes to 0 by compactness, the inverse goes to infinity. So I mean, so this is basically proof of part A. I mean, it's exactly proof of part A. Okay. Now part B. Okay. Now, what about the smoothness? I still haven't done smoothness. Also, we have to note that these lambda n's are smooth, and in fact, this is exactly the kernel of an elliptic operator. So that's a smooth. Okay. Also, since I mean not lambda and phi n, sorry, so phi n belongs to kernel of p minus lambda n, and this is an elliptic operator. Because we are just changing the zero order part of this operator, we are not changing the leading part, which would be the symbol. So that's an elliptic operator. So by finiteness and regularity, this guy is certainly consists of smooth functions. Okay. So of course we know that these guys is a form of finite dimensional subspace even without using this compactness argument. But now we want to use smoothness. So phi n's belong to C infinity of or smooth. Okay, so this finishes the proof of part A. So this is part A is done. Now part B. Well, I mean, part B is kind of delicate, right? We have to prove that they go to infinity at a polynomial rate, at least. So they are at least, they grow at least as fast as a polynomial. At least, I'm not saying exactly, but we have to prove. So for this, we can start, we can replace p by p to some power k if needed. But then you notice that the order of this guy, right? I mean, degree of p, pk, is equal to kd. And then I can pick k in such a way that this is bigger than n over 2. Pick k such that this is the case, right? You can always do that, of course. But now I prove the estimate for this operator p to the k, right? So can assume that degree of my operator bigger than m over 2. So if I can assume that degree of p is bigger, if I can prove for such operators, then if the reason for this is that of course the eigenvalues of p to the k are lambda, are eigenvalues of lambda to power k. Right? So for this one, I mean, it's lambda is equal to lambda of p to the k is basically is eigenvalues of this guy to power k. So if you prove an estimate, which is polynomial estimate for this one, you can prove polynomial estimate. Because that delta, I didn't say what delta is. I just said there exists a delta such that lambda n, absolute value of lambda n is bigger than or equal to n to the power delta times. So you can prove it for that, and that's it. Okay, so we just assume. Of course, you know why we have to assume, or why this could be useful, right? This comes from Sobolev lemma. Remember, we needed at one stage to be degree to be bigger than half of the dimension of the space for Sobolev-Lemma to hold. So that's that will come handy. So this is what we assume. But now we can use, we can continue, and we can use guarding inequality plus Sobolev-Lemma to finish the proof. Okay, so I can just say now norm phi infinity okay, so let, of course, this is the subnorm of the function, right? So this is the sup of norm of phi of x, fiber-wise norms. You take fiber-wise norms of this section, and then you take subnorm over all the points. So this is definition for any phi belonging to C infinity of E. So now we can derive this. Then norm phi infinity is less than or equal to some C. Norm phi d less than or equal to C times norm P of phi L2 plus norm phi L2. Okay, so now this part is Sobolev-Lemma. That's why I needed that this degree to be bigger than over 2. So this is Sobolev-Lemma. I mean, Sobolev-Lemma was not formulated like this. It said that if you have an element which is in H k for k bigger than m over 2, then that element is actually a continuous function. That was, but during the proof, I had to prove something like this. That for an element in phi d, if d is bigger than m over 2, so this is d, by the way. If d is bigger than m over 2, subnorm is less than or equal to the d Sobolev norm. That's what I have to prove. So maybe I should say from proof of Sobolev-Lemma. But this is equivalent to this, from proof of Sobolev-Lemma, you have that. And this is what I proved. I'm not sure I called it guarding inequality. Maybe I said it's guarding inequality, but this is what we proved. So this is standard guarding inequality. Okay, so we have this this estimate. So now let f of a. So this is an argument which is due to Gilkey, and Gilkey attributes it to someone. I forgot his name. So it's a kind of a smart argument. So let me just recall Gilkey's argument. So let f of a be equal to a span of phi smooth sections in C infinity of E such that phi is an eigenvalue function, rather. Is an eigenfunction. of an eigenvalue lambda with absolute value of lambda less than or equal to A. So this is for any A bigger than 0, you define this space. This is a finite dimensional space because we are just taking all eigenfunctions that correspond to eigenvalues that are bounded by A. Well, these eigenvalues are going to infinity. So there's going to be finite number before each A, right? There's going to be finite number before each A. And each of those eigenvalues have a finite dimensional eigenspace. So this total dimension, which is of the space f of A, is finite. So this is space f of A is finite dimensional. We're just looking at the initial part up to some point of the spectral decomposition. That's what we're doing. Just initial part of the spectral decomposition. So this we know. Okay, then what? Now I can say the following from that kind of estimate. So we know that norm by infinity is less than or equal to C regarding, so this is E phi L2 plus norm phi 2. So this is less than or equal to C times absolute value of lambda n plus 1 norm phi L2 for any phi belonging to f of A. Now, what is this n? So let n equal to n of A be equal to dimension of fa. Right? I mean, all eigenvalues are less than lambda n, corresponding to eigenfunctions that are in fa. And then we can write this estimate. That's pretty easy. Right. So now, so we are over a vector bundle. Then the argument is that first assume that your bundle is actually a trivial line bundle. So it's a trivial line bundle. So basically, this P is a scalar operator, right? P is a scalar. Okay, then you can just say that for any Cj belonging to C, we have norm some Cj Ij of x over j between n and 1 is less than or equal to C times 1 plus absolute value of lambda n times some absolute value of Cj squared 1/2. I mean, we are just using orthogonality of this, in fact, orthonormality of this phi j's. This computes L2 norm on the right-hand side. And then for this one, you just use lambda, and for this one, you just compute this. Okay, so now we have that. So then Question? It's an easy estimate. I mean, follows from the way things are set up. So let Cj now be equal to phi j x bar. So I should say for any x belonging to n, let Cj be equal to. So we just pick those particular values for some x. We just take Cj to be that, right? Then this gives us, then we get that sum. Here you just replace, you get sum of norm of phi j x squared j less than n, 1 is less than equal to c times 1 plus the value of lambda n. Maybe I just continue here. Times some absolute value of absolute value of phi j x squared, j from 1 to n, and then 1/2. But this right-hand side can be estimated as follows: sum norm of phi j x squared j between n and 1 is itself less than equal to c squared times 1 plus lambda n squared. Okay, so I should not say but. That's a wrong thing to say. I have this less than equal to that, and then I want to conclude that this is actually gives us another factor of c times 1 plus lambda n, so that overall I'm going to get this is less than equal to that factor. You see, these are L2 norms here. No, they are not L2 norms. They are absolute values. Yeah, they're not L2 norms. They are absolute values. Okay. So no, certainly I want this. I want this without norms for any x. And by choosing Cj's to be like that, I want to have that less than equal to, so what is on the right hand side? Yeah, that right hand side is okay, C2 times 1 plus lambda n squared. That's okay. But here I want that. So now, what is this estimate here? This is norm infinity. So it just means, so this is also wrong. So because that's norm infinity, so I just replace phi by this guy. So this should be that, right? And then I choose, okay, I choose Cj to be phi j bar x, then I get this So far, we have that for any x. Right? Now we're going to integrate over n. Right? So integrate over n. So if you integrate over n, you know. Well, I mean, what you get on the left-hand side, on the left-hand side, because this is still a inequality. I mean, there's x dependence here. So I want to integrate this inequality over n. Then what you get on the left-hand side, well, this gives you L2 norms of phi j's, but phi j's are orthonormal. So L2 norm is 1. So we get n on the left-hand side. So let me put it like this: integral of this, so maybe integral of left-hand side is less than equal to integral of right-hand side. So this gives me, but left-hand side, it gives me n, right? Is less than equal to C2 times 1 plus absolute value of lambda n squared times volume of n. Because right-hand side is x independent. It's just a constant. Right? It just depends on n, but it doesn't depend on x. So you integrate, you get volume, and this is, so this is. So if you believe in this up to here, then the rest is something. Okay, so, and this of course implies that lambda n is bigger than or equal to c and delta for some delta positive, some c positive. I mean, this just immediately implies what you want, right? That's immediate. Okay, so this takes care of the situation. This nice trick takes care of situation for trivial line models. So for trivial line models, we settle that. Now, for any question?
Yeah, there's something that bugs me about that equation. So if you,
which equation?
The bottom one on the left.
This one?
Yeah.
Right.
Because if you were to scale phi.
Oh yeah, this is still, I should not have this, so I should have this. It's like that, because everything just depends on point x. These norms I put are wrong, yeah. Okay, then, yes.
So this may be not something that we can do because the phi's are orthonormal. But if you were to scale the phi, the left-hand side scales quadratically, and the right-hand side scales linearly.
Yeah, but these phi's are definitely orthonormal. So I use that at the end, actually.
Yeah, but not to get an equation.
Yeah, but yes, so, okay. Absolute value of Cj square. Yeah, okay, so that's not. Yeah, we cannot, I should say we cannot scale it because it has to be norm 1. Yeah. So if you scale it, you lose norm 1 condition. And indeed, I use this norm 1 because I'm, in computing L2 norms, I use orthogonality of these phi n's in order to say that this is like this one, for example.
Yes.
If you don't assume orthonormality, you don't get this. This is like in, Fourier expansion. This is like Parseval. This is like Parseval. Yeah. Otherwise, we won't have something like Parseval. But that's a good point. Yeah, one should. But I mean, this stuff is now. If you, I mean, that's easy to verify now. But the main thing is the trick, is kind of interesting trick. Okay, so now, any other comments or questions? Okay, so now what I can say is the following. So the next step would be to go to trivial rank K bundles, which are not difficult. So this is, after all, just for trivial line bundles, right? I mean, some argument has to be given, but do it for E equal to M cross CK. And then in general, E is locally trivial. Once you prove it for this trivial rank K bundles, you can use partition of unity and reduce those cases. Use partition of unity to reduce. So, I mean, there is some argument you have to give, some details, but that's the idea. The main thing is just to do it in this case. I mean, that's the main thing. Okay, so I won't go into more details because that just takes time. So, and you can check in Gilkey's book in like 95 edition, I guess, the final edition, which is pretty good. Okay, so that's very good. So now we have what we wanted. So we have this L2 decomposition. We have at least some a priori estimate for these lambda n's. I mean, I should say that. And smoothness of eigenfunctions, finiteness of space of, you know, for each eigenvalue, corresponding spectral space is finite dimensional, all that. So, okay, so this is the spectral decomposition. But I mean, so I did some examples, but let's do some of these examples maybe again in some detail and then move to git kernels. Okay, so example 1. Let's take S1 to be equal to R mod Lz. So L is some positive number, right? So this is a circle of length L, right? It's a circle of length L. Length L. And let's take E to be equal to S1 cross C as we did over there, and D to be this 1 over I dx operator, right? So the spectral decomposition in this case, so what are the eigenfunctions? So D of phi equal to lambda phi. Immediately you can solve this equation, you get that phi is equal to phi n of x is equal to e to the, 2 pi I n over L x, right? So now I have to put some constant Cn here to make sure that this is orthonormal and n belongs to z, right? So lambda n, you know, of course, you see that this is periodic for this L lattice. So lambda n is equal to, well, what is lambda n now? So lambda n is equal to, so if I apply, right? And so you just apply this 1 over I dx to this operator, you're going to get 2 pi n over L, right? N belongs to Z. And these eigenvalues are simple eigenvalues. There is no multiplicity, right? So no multiplicity. Multiplicity. So these are simple eigenvalues. Okay. So we have that. Of course, here everything is a result of Fourier analysis, right? That's what we learned in Fourier analysis. We learned that L2 of S1. So independently, analysis implies that these guys form an orthonormal basis for L2 of S1. E to the n over Lx n belonging to Z is an orthonormal basis. I did not compute Cn. Let's compute Cn, but it doesn't add anything to our understanding of the situation. It's better to think of this growth of eigenvalues like this. You see, here eigenvalues lambda n is growing like n. So this verifies also the growth that we had. But this is even much better, actually. So note that the value of lambda n is equal to 2 pi absolute value of n over L. So the eigenvalues are inversely proportional to length of your manifold, or volume of the manifold, and they are growing linearly with respect to the index. In this case, it's linear because it's a one-dimensional manifold. That's the reason. So this everything in this case is very, very straightforward. We didn't need the general result for decomposition. Okay, so okay, of course, I mean this 1 over L is this dual lattice, right? So the dual lattice is 1 over Lz, right? That is Lz. I think I used the notation star maybe for my lattice duality. This is the dual of this lattice Lz. I mean, this, you know, there is no accident that there is 1 over L. It's always is that you know, comes from the dual lattice. So okay, so that's for first order operator in this case it was. So and then we also looked at Laplacian for general lattices. So this is example 2. So in this case, degree of D. We want this to get case where degree of D is equal to 2. As I said, we can look at M Rn divided by lambda. Lambda inside Rn is a lattice. So in other words, it means that there exists a basis, not an orthonormal basis, just n vectors, linear independent vectors. Z1 plus Z, so i.e. ZB2, ZBN Any2, just the basis, not an orthonormal basis or a standard basis. I mean, just a basis for. And if you take different basis elements, you do get different lattices. Okay, so that's our manifold, and metric is. So there is this, of course, Rn over lambda. So this is a covering map. So you can push forward the flat metric here to the metric on the quotient space. So flat metric on Rm over this one. And let's take D to be delta to be D star D. It turns out to be equal to minus some d dxi, d2 dxi squared. So this is the flat Laplacian for torus. So this is the flat Laplacian. And eigenfunctions in this case, of course, are parameterized or indexed by the dual lattice, right? And eigenfunctions and eigenvalues are indexed by the dual lattice lambda star. This is the dual lattice. So in other words, if you want to solve this equation like Laplacian of phi equal to lambda phi, you can easily show using Fourier series and other things, you know, that this phi has to be of the form some constant ck exponential of 2 pi I inner product of x with k. But this k now belongs to the dual lattice. So I'm going to call this now, recall its definition. So this dual lattice, remember, it was the set of all x belonging to Rn, such that, well, maybe y belonging to Rn, such that inner product of x and y belong to z for all x in the original lattice. Belongs to z for all x belonging to the original lattice, lambda, right? Okay, so now you notice that if you move on this lattice, if k is in the dual lattice, now if you move on the original lattice, once you change from one period to another, then you get a periodic function. So it's got to change. Because that's an integer, so this. Okay, so now the question is what is the eigen, well, ck is a constant that you can compute, depending on the co-volume of the lattice. It doesn't matter. Now, so the question is, what is the eigenvalue then? The eigenvalue, you can compute this I mean Laplacian over here. So you're going to get equal to 4 pi norm of k squared. Because you have to differentiate this twice, you're going to get norm of k squared. And 4 pi squared, by the way. Yeah. Okay. So this is for any k belonging to the dual lattice again. So let's, I mean, for example, if lambda is equal to Zn, the standard lattice. So eigenvalues are going to be then of this form. Lambda is equal to lambda k is equal to the set of all n1 squared plus n2, so n1 squared plus n2 squared plus nn squared. And I belonging to Z, and so yeah, I mean they have to add up to 1/4 pi squared times this. So anyhow, so maybe I'll just put it like this: 4 pi squared times this thing. Now, anytime you pick up same numbers while moving over the lattice, you're going to have a same eigenvalue, right? So the multiplicity of this eigenvalue is the number of ways that you can represent an integer as sums of squares, essentially. So that's the relation to number theory and theta function. So let me write it. So the multiplicity of an eigenvalue, so I'm going to write the eigenvalue like this: 4 pi squared times lambda, for example, is the number of ways is equal to number of ways that can represent the integer lambda as sums of squares of integers, sums of n squares actually, right? As the sum of n squares, right? So so for example, there is a famous theorem of Lagrange that says that for n equal to 2, any integer, non-negative integer, is sum of squares. So this number for all integers, all integers are multiplicities. So this is a result of Lagrange. Because I use lambda, so well, lambda is a kind of disaster notation for an integer, but that's okay. Any lambda bigger than equal to 0 belonging to n is a sum of 4 squares, right? You can always write this lambda as n1 squared plus n2 squared plus n3 squared plus 4 squared. So this immediately goes into some number theoretic issues. It's related to number theoretic issues, this question on lattices. I mean, for n equal to 4 on this 4-dimensional lattice, this always has a solution. And but what is interesting is to know in how many different ways. And that's the multiplicity of the problem. But in how many different ways? I won't give you the answer. I don't remember the answer, but the answer is related to these divisor functions in number theory. So it's so we will discuss this in the course. course, in the spectral geometry. That's very much related. Now, for n equal to 2, it's not true that any integer is a sum of 2 squares. That's not true, but some integers are sums of 2 squares. So, for example, primes of the form 4p plus 1 are sums of 2 squares. That's a famous theorem of, I believe it was proved by Fermat. Or maybe rigorously proved by Euler, I don't know. So let's not get into that. So again, this orthogonal decomposition in this case is a result of Fourier analysis also. So again, spectral decomposition follows from Fourier analysis. So we don't need that general result in order to prove the result of this theorem in this case. Now, there is a case that I'd like to discuss. Maybe Jeremy can look at it and then find an answer. You have to do some literature search, Jeremy.
Okay, what am I searching for?
So, well, you have to search. You don't know? You don't know yet? Okay, so the search is the following. So this result can be generalized to all compact connected D groups. So this is a non-abelian version. So let me write it. Non-abelian case. So let G be compact connected D group. Okay, so the analog of this orthogonal decomposition in that case is this famous Peter Weil theorem, right? Peter Weil said that this L2 of G, right? Oh, yeah, actually, that's Peter Weil. You're an expert. You were talking about Peter Weil the other day. Now you're an expert on Peter Weil. Yeah, so this is, so there was a reason I chose you to. Now I understand why I chose you. Okay, very good. So L2 of G is equal to direct sum of, remember it was like E tensor E star or something like that? E lambda, what's a good notation? Maybe E lambda, tensor E lambda. Well, lambda belongs to G hat. So this G hat is the unitary dual, right? So this is the set of all irreducible unitary representations of this compact connected group G, which is a discrete set. That's what we know. And this is essentially the space of matrix coefficients. I mean, this is like endomorphisms of this space, this matrix coefficients. I mean, this is kind of abstract way of talking about pick a basis in your representation E lambda, and then write these matrix coefficients of your representation function, and then so anyhow, so this is but the thing is, this is an orthogonal decomposition. This is, so maybe I should say you have to complete it, or maybe I put like something like that. So this is a Hilbert space sum. Hilbert sum. I don't want to put another bar here, which should look ugly. This is a Hilbert direct sum. Anyhow, so this is a decomposition of L2 of G into some orthogonal. So you have got some God-given orthogonal functions, almost God-given, because still you have to choose a basis in this case. Okay. Now my question is that are these things related to eigenfunctions of some Laplacian on G by any chance? Because in the abelian case we know that they are, right? So my question is this now. So let's call this maybe star. So the question is star a consequence of spectral decomposition or a Laplacian delta on. Now we are talking about Laplacian, so you have to ask for which metric, right? So which metric we have to choose, that's your job to find which metric, if there is such a metric. And then, and also this question is known, it's not unknown, you have just to do search. And then, at least for some Lie groups, this might be true. You have to find those Lie groups where this is true. And so your task would be to relate eigenfunctions of Laplacians to this sort of matrix coefficients of Erems. You see, in the abelian case, we have complete correspondence, right? I mean, the fact that Laplacian of e to the I n x is equal to that number times e to the I n x, and e to the I n x are Fourier kind of basis for L2 of e. It's not accidental. I don't think it's accidental. Anyhow, so I don't want to. So if you have anything you want to understand, just ask me later, so I can tell. So I think now we can just stop talking about orthogonal or spectral rather decomposition of L2, because we have a lot of examples now. So I want to go now to the next topic, which we need. And that is, oh, I didn't bring my coffee. Oh, that's bad. Yeah, but this is from last week. Alice, you want to kill me? No, actually, this is so. That's completely dried. Still, I mean, coffee is. It may be poisoned, I don't know. Okay, no, this was a good suggestion. Okay, so now what we want to do is start talking about, unless you have questions, otherwise we move to heat equation and heat kernel. That's the next thing we need. Heat kernel. Okay, so now, what's the setting again? The setting exactly is what we had. So we have, setting is as before. So we have this P, C infinity of E to C infinity of E, except that now I'm assuming that this P is self-adjoint and is non-negative. So spectrum is bigger than or equal to 0. And spectrum of P is inside R plus. So this is a non-negative or positive object. Okay, anyhow, so these lambda n's are all bigger than or equal to 0 for all. So that's what we are assuming. So now the heat equation. So the heat equation now is the following equation. Is ddt plus T phi equal to 0. Phi now is, so it is a section of this bundle cross, I would say maybe, so I'm going to actually say bundle E tilde. So E tilde now is a bundle over M cross R. So basically, this phi is a function of two variables. One variable is in M base, and the other one is T. So I would say even this is bigger than or equal to 0. So this is the equation, this is the heat equation. And now there is also, if you want, there is also a boundary condition. So the boundary condition is that, so the boundary condition should be that phi at x and 0 is equal to phi 0. The initial heat distribution is given. So that's the initial temperature. Temperature, I would say, what? Temperature in the sense of vector bundles, temperature distribution. Okay, so I mean, the idea is that you have an initial section, phi of x and 0 is just a section, initial section. And then you want to evolve this section in time following this evolution equation. So this is some harmonic evolution equation, right? Harmonic evolution. Okay, so now the original heat equation, of course, I mean in Rn. Let me just maybe heat equation in Rn. You remember the heat equation in Rn? It was like ddt u is equal to Laplacian of u, right? That's the original heat equation in Rn. Well, Laplacian in that case, though, is sums of. This is not geometer's Laplacian, analyst Laplacian, sums of di squared. So have this in mind. Of course, in this case, E at the bundle is just the trivial bundle, right? I mean, Rn cross R, the trivial bundle. And this is called the heat equation or diffusion equation. And there's some coefficient here, it's called diffusion constant. And that's kind of governs distribution of heat in time. As time evolves, heat goes from hot places to cold places, and it kind of balances itself according to this. So this is due to Fourier, of course. And this is a generalization of that thing. Okay. Okay, so now Now, of course, you have to ask why you care about this now, all of a sudden, where this equation came from, and why this equation should be relevant to geometry and to index theory and to these things. So, yeah, we have to address these questions slowly. Any questions or comments?
I might have missed when you said this, but why does ddt t times b? How does that?
Oh, no, this is plus. I'm sorry.
Oh, it's plus.
This is plus. Yeah, this is plus, of course.
Yeah, sorry.
It's like here. You bring it to the left-hand side, and that's your p, because the actual p positive operator is minus Laplacian, not plus. That's right. So now a solution for this, of course, is immediately available. We can write down the solution, at least formally. So solution exists. Now let me write it like this: formal solution. Well, I mean, this is going to be e to the minus tp. Phi 0. I call the initial condition phi 0, I guess, right? So phi 0, right? So now the question is, what is this operator e to the? Well, I mean, formally this satisfies the equation. As always, with parabolic equations, you know. But the question is, what is e to the minus tp? What is this operator, right? So this, of course, I mean, is supposed to be a bounded, a very nice operator from L2 of E to L2 of E, but how we can define such an operator? That's the thing, right?
I have a quick question before we continue, if that's okay. All right.
Sure, of course.
When you say the setting is as before, did you mean in terms of the decomposition theorem with like Hermitian vector bundle over compact
Yeah,
manifold?
exactly, right.
But the example of the original heat equation was over a non-compact manifold with a non-Hermitian vector bundle. Can we like?
You speak louder, please.
Oh, sorry. So the original heat equation, like the classical heat equation on R to the n, that's like over a non-compact manifold, and the bundle is real, right?
Yeah. So right, the original. I mean, the actual heat equation is on Rn to start with, but then you can look at it on some bounded domains on Rn with further boundary conditions also.
Sure, right.
And you can also look at it on compact manifolds. So to get the analysis going, we have to assume our manifold is compact.
Okay, just checking.
And in fact, to do it over non-compact manifolds is a much more subtle issue and much more complicated issue, in fact. Because in that case, you don't have discrete spectrum. In that case, you're going to have some sort of continuous spectrum, and that creates all kinds of issues. Okay, so now what is this operator? But in fact, we have this, yeah, indeed, related. In fact, we have now this spectral decomposition of P. So to define this, I use a spectral decomposition of L2 of E. Well, we have an orthonormal basis, right? Consisting of eigenfunctions of P, right? This is this thing that we have. Well, okay, let's. I mean, P of phi n is equal to lambda n phi n. But lambda n's are non-negative, right? Lambda n's are. Now I can define exponential of minus tp on these phi n's to be e to the minus t lambda n over phi n. So basically what happens is that you have kind of diagonalize your matrix P, and of course any function P can be defined like that. So e to the minus t p phi n, let's define it to be e to the minus t lambda n phi n over all n. So this defines that e to the minus tp from L2 of e, L2 of e is defined. Not only is defined, you can immediately see that the eigenvalues as n goes to infinity is going to 0, right? Now the eigenvalues, the eigenvalues are these ones, right? For any t positive, e to the minus t lambda n goes to 0 as n goes to infinity, since lambda n is going to infinity, right? That. So this is a compact operator. This is a compact operator. Not only is bounded operator, but in fact it's compact operator. Compact. In fact, we will show that it's a very, very special kind of compact operator. It is in fact a smoothing operator. It sends L2, all of L2 into C infinity of M. In fact, it is a smoothing operator. So, so in the following sense, for example, I'm going to show that there exists a kernel here. There exists a kernel, a smooth kernel, K, T, X, Y. So this belongs to C infinity of. Now let's assume for simplicity that P is a scalar operator. I don't want to introduce extra notation right now. Just C infinity of, C infinity of, I would say, M cross R. So I'm assuming P is scalar now, for the moment. So there exists a smooth kernel such that in fact, e to the minus tp phi of x is equal to integral over m k of txy phi of y devolving over this one. Right? So it follows that, of course, as a result of this operator having a smooth kernel like that, of course, it follows that this maps L2 of E into C infinity of E. Right? E to the minus TP maps L2 of E into C infinity of E. I mean, I'm doing it now for scalar operators, but I will write down the kernel in general, and then you notice that general is smooth. So this, in this sense, very precise sense, is a smoothing operator. The kernel is a very nice. So, oh, sorry, this R, oh yeah, this is bad. Positive, strictly positive. I cannot say anything at 0. Strictly positive, but it's a smooth one. M cross R. Okay, so that's what we have to do. Now, in this case, you can write down the kernel using exactly the method of separation what's it called in applied mathematics? Separation of variables, right? So basically, kernel, so lemma is this, let k t x y be equal to sum exponential of minus t lambda n phi n of x phi n of y. Maybe I have to put phi n y. And from 1 to infinity. This series is uniformly convergent. Its derivatives also are uniformly convergent. This series same for derivatives of right-hand side. Now, to show uniform convergence in this case is not bad because we have these estimates on lambda n's. Lambda n's grow polynomially, right? So that and then basic thing can show you that this. So let me just say this follows from the estimate that we had that lambda n is bigger than equal to c n to the power delta. Basically, norms of this subnorms of these functions and subnorms of the derivatives and all these things are going to be controlled by this sort of system. So this is not difficult. Okay, so now it's a method of separation of variables. It's very easy to check that actually this is indeed a kernel. That you know, e to the minus k y is indeed the kernel e to the minus tp. Remember, we defined e to the minus tp by these rules. E to the minus tp phi n is equal to lambda and phi n. That was the right. It was defined at first to be e to the minus t lambda n phi n, right? That's how we defined it. So you have to check that integral kt xy phi n of x d volume is equal to this guy. Well, this is given by this sum here, right? But then you can separate the integral and you use orthogonality of these functions, and then what you get follows, right? So that's easy then. Okay, so that's that's very good. So we know that there exists a kernel. The kernel is smooth, and it matches with our original definition. And actually, if you have any initial condition, this will give you a solution in all positive time. So now this is for just a scalar case. But you can easily define what the kernel is for bundles. Yeah. So what is a kernel in general? That's not difficult to guess, right? I mean, any question by the way so far? Maybe I should give an example of this kernel. Just give an example. That might be. So Jeremy is going to complain, says that your example is going to be on Rn, is not compact. But I will give you an example on compact space then after that. Okay, so let's. No, I think it's a good idea to give an example. This example is very important. So. So example. So this is heat equation on R. Right. So this is the equation. E to the T. What is E to the T? Sorry, E to the T. U. So let me write it like this. Ut plus, or rather minus uxx equal to 0, right? So this is the heat equation on the line, on R. So what is the kernel of this? So K E x y is equal. Anyone remembers the kernel of this algorithm? So you need a function of t, x and y in R. Name of a famous mathematician is attached to that. It's the Gaussian. So it's 4 pi t to the power minus half exponential of minus x minus y squared over, I believe it should be 4t, but there may be some correction needed here, but I believe this is correct. That's it. That's the kernel. So it's a Gaussian. So this is very important because we will see that in general. I mean, so our goal is to reach to something like this for general manifolds. And in general, we'll see that for general manifolds, there's going to be this plus infinite number of corrections. And those corrections contain all the geometric information of the manifold, essentially. So we have to get all of them. But this is for flat space. Now, when I say this is the kernel, what do I mean, really? What do we mean, really, to say that this is the kernel? Because this is not a, so now Jeremy's complaint is quite valid in this case, right? Because what do I mean to say this is the kernel? I don't have an orthonormal basis. I mean, there's no discrete basis, right? So, because I mean, to say that they are obtained from some sum e to the minus t lambda and phi n x, phi n y, that doesn't make sense because I don't have such decomposition. Because that's a non-compact space. So you're very right to complain here, actually. So what should we do? What does it mean that this is a heat kernel? So there is a different definition of kernel, which I will write down. And the two definitions are actually equivalent. And you will see that this is. So K is a kernel in the sense that it is a fundamental solution of the heat equation. it is a fundamental solution. So that's a very important concept, solution. Of the heat equation. So it's in the following sense now. So for any y, i.e., for any y belonging to R fixed, right? For any fixed y, ktxy solves the heat equation, first of all. The solution of this heat equation, ddt, plus minus kxx equal to 0. So this is the calculation you have to do. That's very important. Please do this calculation. First of all, this solves. Second of all, when you approach, when x approaches, when t approaches 0, this family of functions approaches the Dirac mass at y. And kt of x and y approaches Dirac mass at y as t goes to 0 plus in the sense of distributions. So in other words, we want to say that k0 xy is just delta mass at y. So what is the physical intuition for this solution? The physical intuition is this. At y, you put a unit of heat at time t equal to 0, and you let this to diffuse. So it's like you have some like water, and then you introduce a small piece of ink, chunk of ink, you drop into the water, and then you let it diffuse. If it is a diffusion equation, it's going to be like this. Of course, we can never approximate delta function. We can approximate delta function, but we can never reach the delta function. So, but in this sense, you see that if you get better and better to delta functions, this approximates the behavior of diffusion in time better and better. Okay, so there are two things here you have to check. First of all, this is the calculus aspect. You have to check this. This is this is for t positive, right? And x and y belonging to R. That's we can check. This is calculus. It's kind of lengthy, but you can check. But this is in the sense of distribution. So you have to check that this function approaches to this distribution as t goes to 0. Another thing, there's beautiful things, pictures about these things to have in mind. Another thing is that what happens to this guy as t goes to infinity. As t goes to infinity, this piece of ink at that point diffuses and becomes eventually 0 everywhere. Of course, you have to expect that because it's just so thin eventually. There are many other surprising things about this heat equation in this case. For example, at time t equal to 0, there may not be any pieces of this except at y, a neighborhood of y, which has non-zero temperature. Temperature could be 0, but immediately after 0 time, the temperature is non-zero. So this heat is very unrealistic also. So it propagates with infinite speed, right? So this heat is not realistic, but it's something that applies to So if you want to do a relativistic heat equation, okay, maybe that might be, well, that would be perhaps a vague equation. I don't know. Anyway, so this is in this sense, in this precise sense, it's a heat equation. It's a kernel again. So we have two notions of kernel that we have to relate somehow. And then another thing is that, well, the question is this unique? Is it unique? Well, I mean, it doesn't have to be unique, except if you assume that there is some condition at the infinity. If it decays fast enough at the infinity, you can show that this is the only solution. Otherwise, you can take, you can add some non-zero at infinity function to this, which would be the kernel of the operator, and that still satisfies this. So uniqueness is a bit delicate, you have to be careful. Okay, now, in the last 5 minutes, I'm going to give you the exact equation for the heat kernel on the circle. Now, circle is compact, so we can relate to what we know from eigenfunctions or Laplacians. So this is one example. So this example, okay, by the way, let me write this for Rn. Maybe I'll just finish with writing this for Rn, that's important. So this is another example. Rn, so this would be k e xy is 4 pi t to the power minus n over 2. Exponential of minus norm of x minus y squared. Again, over 40. So that's the heat equation. That's the heat kernel. In this case. So this is a very, very important kind of paradigm to have in mind. I mean, this is very, very deep. There's a lot of meaning. Also in probability theory and a lot of stuff. So that's okay, so let me just finish by giving you on the circle, the thing on the circle. M equal to S1. So let's take a circle of radius 1. It's a circle of radius 1. In this case, ktxy is a sum and belonging to z exponential of, well, there is this by t. So let me write it here. Let me write it in this case, it's this one. It's the infinite series. Now, I'm a bit worried about the factor of 2 pi. because this has 2 pi period. So maybe I just define it by z. That's better because I'm just periodizing by adding a factor n here. So that's better. That's it. So you see, it's an infinite sum, and it's. So next week we shall look at heat trace, and we shall look at expansion of the heat trace. Question? First of all, I mean, you have to check that this is a periodic function in x and y, and it is the way we have done it. I mean, so this is periodic, first of all. That one, and then also we need to check that. Yeah, I mean, in this case, this is the heat kernel in both sense, in the sense that it's obtained by summing over all eigenfunctions in that case, and it's also, yeah, in the sense of heat diffusion also. 4 pi t minus half. Yes.
Earlier we had this formula for K as the sum of over the eigenvalues e to the minus t eigenvalue phi n of x, phi n of y.
Lambda n, phi n x, right?
Yeah.
Phi n y over n, right?
It feels to me like these things are different, or I find it hard to believe that these sums will be the same.
Right, they are the same, and in fact, the fact that they are the same follows from Poisson summation formula. Yeah, you're right. It's not clear that this is equal to that if we do this. That's a very good point, in fact. We'll check next lecture that by applying Poisson summation formula, you can check that the thing that you get by brute force original method and the thing that we got by averaging the heat kernel from covering space. You see, here there is this covering map, right? We have the heat kernel here, and we did an averaging over the action of Z. We got a heat, we push it down, we got a heat kernel here. So this is the method of averaging, that from here, so this was averaging. Indeed, you raise a good point that this is also available in this case because we know exactly what phi n's and lambda n's are. After all, what is lambda n? Lambda n is, in this case, is 4 pi squared n squared. And we can index them by z so that the multiplicity is taken care of. Right? And then what is phi n? The phi n, you remember, it was exponential of I mx, maybe 2 pi I, 2 pi I, 2 pi I. Again, it belongs to z. Cool. So if you do this thing, there's of course conjugation. So the conjugation, if you put, so you get this is equal to sum n belonging to z exponential of minus t times 4 pi t 4 pi squared n squared, exactly. And then we have got exponential of 2 pi I nx exponential of minus 2 pi I ny. So this becomes exponential of 2 pi I n x minus y. But I still have that term here, which doesn't look like this term. That indeed I'm worried now, actually. So we have to. So yeah, this is a good point, actually. So yeah, Poisson summation formula would be very useful here, but still I'm a bit worried in this case about this first order term. Okay, so no, I think that's a good point to start now, and then this I will do next time. But that's a good point to stop. So Jeremy, you have any complaints? No complaints. But we have a lot of complaint now about this. This is the last statement, so we have to see how it works. So I just stop.